Hello everyone, in this video we're going to pick up where we left off in section 12.1 and example 4. Sketch the plane curve represented by the vector valued function r of t equals 2 cosine of ti minus 3 sine of tj for t between 0 and 2 pi. Okay, so just as before, when I had, when I have any function, I plug in a t and I get an I and j. So I'm gonna set this up kind of like how we did our parametric equations. Ironically, or not at all ironically, because that's really exactly what this is. Remember, vector valued functions are really just parametric equations. Right? So I'm going to plug in different t values and I'm going to get different I and j values that will represent a vector. Right? This will be, whatever I get here will be something I and the other one will be something j. Right? So t is from 0 to 2 pi, so let's go 0, let's go pi over 2, let's go pi, 3 pi over 2, and 2 pi. So if I do that, if I plug in 0, cosine at 0 is 1, so I get 2. Sine at 0 is 0. Cosine at pi over 2 is 0. Sine is positive 1, so I get negative 3. Cosine at pi is negative 1, so I get negative 2. And sine at 0 is, sine at pi is 0. Cosine at 3 pi over 2 is 0. Sine at 3 pi over 2 is negative 1, so negative 1 times negative 3 gives me positive 3. And then I would get 2 and 0 here. Okay, so one thing that, or let's go ahead and sketch this. All right, so if I were going to do this on a curve, I'm going to have 1, 2, 1, 2, 1, 2, 3, 1, 2, 3. Okay, and so I go to graph my first one here. It's the point, or it's the vector 2, 0, right? So that is this vector right here, 2, 0. So I remember it corresponds to that vector right there, but I write the point right on the terminal point of that vector. And then I have the vector 0, negative 3, so that one points downward, right? It has negative 3 in the j direction, so that's this point down here. And then I have negative 2, 0, so that is this vector right here. And then I have 3, 0, so that is this vector right here. And then I go back to 2, 0, right? So my graph ends up looking, if I can draw this, okay. My graph ends up looking like that, and it would have like all these vectors right in between there, right? Maybe I'll draw them down here, right? This would be on there, this vector would be on there, right? But really all we're interested in is the curve, right? And which way did it go? Well, this was t equals 0, this was t equals pi over 2, so it went this direction, right? The orientation, maybe I'll put that in a different color. The orientation was this direction, right? If I had instead thought of this as a set of parametric equations, then what I would have gotten was I would have gotten the parametric equation x equals this first guy, which is 2 cosine of t, and y equals the second guy, which is minus 3 sine of t. And I would have just gotten a set of parametric equations for x and y points, right? It would be 0, pi over 2, and I'd still get the same points, right? 2, 0, 0, negative 3, negative 2, 0, 0, 3, 2, 0, right? So this would pi, 3 pi over 2, 2 pi. And when I drew the graph here, it would look like this, 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 and this. So it'd still be the exact same graph. The only difference is we just lose this idea of having vectors instead of points. But really, remember, this is a plane curve represented by a vector valued function. So really, all we care about is the curve, right? So these vectors on here, I really could have gotten rid of, all these little vectors. I don't, just because I want to rehash the fact that it is a vector valued function, but really I could have thought of it as a set of parametric equations and graphed it that way. All right, so again, if I were just to redraw this without the vectors, it would look like this curve right here. It would have the orientation just like this. And again, we just kind of lose the idea that those points represent vectors, but the idea is still the same. Okay, and so let's analyze this a little bit more. So from the position vector, let's talk about this idea of the fact that it's still a parametric equation, either a vector valued function or a parametric equation. The idea is still the same. So from the position vector, from the position vector r of t, we get the parametric equations. And again, I kind of already talked about this, but we get the parametric equations. X equals 2 cosine of t and y equals -3 sine of t. Right? Because we can always think of this as the first parametric equation and this is the second parametric equation. So we want to find the corresponding rectangular equation. Right? So the corresponding rectangular equation, because typically I could either graph it using, I could find x and y points like I did before for different values of t, and as we just showed, that's the exact same as this graph up here. But the other thing we did when we were talking about parametric equations is write the corresponding rectangular equation. And remember, what do we do in this case? Whenever I have sines and cosines for my parametric equations, I always use the property that cosine squared of t plus sine squared of t equals to 1, right? So if I looked at these parametric equations, I know that x over 2 is equal to cosine of t, and y over -3 is equal to sine of t. So this would mean that x over 2 squared plus y over -3 squared equals to 1, which gives me x squared over 4 plus y squared over 9 equals to 1. And remember, when my denominators are different, right, like that, this is an ellipse, right? And and if you look at the graph that we showed above, if I had changed it to rectangular, if I had looked at this vector valued function, changed it to parametric equations, and then changed it to rectangular equation to graph it, I would still get the exact same graph, right? I would just have an ellipse. Or I could think about it as a vector valued function, or I could think about it as a set of parametric equations, right? They're all kind of the same thing. Obviously, when you think about it as a vector valued function or a set of parametric equations, you get orientation, so you get a little bit more information. The other thing to note here is that the curve has clockwise, actually that's not really entirely important in this case, the fact that the direction of the curve, right? We'll talk about direction of the curve a little bit later. Right? So that is a big analysis of the plane curve right there. So how about in the 3D case, right? So sketch the space curve, right? Again, so the idea is we're using this vector value function to draw a curve represented by r of t equals 4 cosine t I plus 4 sine of t j plus tk. Okay, so from the from the position vector, this time we're not going to go ahead and we're going to do some analysis first before we just try to graph it, right? Because in the first example, we just went ahead and graphed it with t and ij values. Now it's going to be a little bit more complicated in the 3 dimensions. So we're going to do some analysis first, right? So from the position vector r of t, we get the parametric equations. Right, we get x equals 4 cosine of t, y equals 4 sine of t, and z equals t, right? Just all these, the first, second, and third equations represent parametric equations, or we can write them as parametric equations, right? And so so we can say, using the first two, parametric equations, we can write the corresponding rectangular equation. So again, we're using x equals 4 cosine of t and y equals 4 sine of t, right? So anytime I do sine and cosine, I should use the fact that cosine squared t plus sine squared t equals to 1. This time, what is cosine of t? Well, if I solved for cosine using my parametric equations, it would be x over 4 squared plus y over 4 squared, because that's what sine would be, equals to 1. So I get x squared over 16 plus y squared over 16 equals to 1. Since the denominators are the same, it makes sense to clear out the denominators and get x squared plus y squared equals to 16. And what's that shape? That is a circle of radius 4 centered at the origin. Okay, so you may be asking, why are we looking at 2 dimensions, right? This is a 3-dimensional curve. Well, notice, what is the third parametric equation? The third parametric equation is just z of t. Z equals to t. So whatever t value I get is going to give me, that is my z value. And remember, z is just where I'm at on the z axis, right? Or my z coordinate. So in other words, just how tall I am, right? So this means, because I know that I have a circle and because my z is just equal to t, this means that the curve we're trying to draw lies on a right circular cylinder of radius 4 centered on the z axis, right? So, because remember when we talked about cylinders, we have this like generating curve that's going to be a circle, and then we just get our height from our different t value, from our z, from our whatever t we're plugging in. So in other words, that's why we have a cylinder, right? So to locate, and then so now again we're going to be on different points on this cylinder, right? So what we can do is just what we did before. Let's take different t values and let's find our different I, j, and k vectors, or we could think about it as finding x, y, z points. So this time, since we're feeling like we want to do something a little different than the elastic example, let's find x, y, and z points this time. Again, it doesn't really matter if we think about it as looking at I, j, k, or if we think about it as just our points on the graph with our parametric equations, right? So t varies from 0 to 4 pi, right? So let's do 0, pi over 2, pi, and then I'm just going to draw like dot, 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 and then we're going to end at 4 pi, right? Because we don't need to do everybody in between. So at 0, again, I'm plugging this into my parametric equations right up here. All right, so when I plug in 0 into x, I get 4 cosine at 0 is 1, so I get 4. Sine at 0 is 0, and then my t value that I plugged in was 0, so z is 0. Now if I plug in pi over 2, cosine at pi over 2 is 0, sine at pi over 2 is 1, so I get 4, and then now my z value is t, so pi over 2, right? So it's the point, it has a height of pi over 2, right? This one had a height of 0. Now when I plug in pi, I get negative 4, 0, pi, right? So in other words, it goes a little bit higher. and still around the circle. So now we would do all those points in between, but the last point would be 4 pi. Well, 4 pi is a multiple of 2 pi, right? So at 2 pi, x is 4, or x would be, cosine would be 1, which means x would be 4, sine would be 0, and z would be 4 pi, right? So it'd have a nice big height. So if you look at this, those are the points that I'm drawing. So I would have this right here would be 4, 0, 0, and then I would have another point up here, right? This point right here would be the point corresponding to pi over 2. And then I would have a point back here, a point up here, a point up here, a point up here, a point up here, a point here, and here, right? So I'd have a bunch of different points on this graph, and my final point here, so my final point is the point 404 pi, right? And again, now that I have all these points, then I can trace the curve that was being, actually I should start at the bottom, right? The curve that is connecting the dots, right? So it would be this picture right here, which I know it's a little bit hard. When I was drawing it, I didn't draw it great, but it's like a helix, right? So what we get is as t increases from 0 to 4 pi, the points spiral up the cylinder to create a helix, right? So again, the curve is what we're interested in. This isn't the equation of a cylinder, right? This is an equation of this curve that looks like, if I can draw it, this curve that looks like this, that goes around and around, right? And that's a helix. Think about like a DNA sequence, right? So this equation, this space curve is a helix. All right, let's go ahead and end this video here. In the next video, we will pick up with the rest of section 12.1.